So let's take a look here at examples number 4 and 5 to see how we can practice using improper integrals of the second type. So you'll see here that we have an integral of a tangent function from 0 to pi over 2, and we're being asked to evaluate if possible. Now if we were to think about what the graph of the tangent function looks like, we might recall that there is actually going to be a shape of a graph that looks like this, but it has a vertical asymptote at pi over 2 at negative pi over 2, and that this general shape can kind of be imagined as copied and pasted all the way down towards the right and towards the left. So we have a problem here in that the area that we're trying to find is this space, but this right edge, the function is, or at the right edge, this function is undefined. So because of this, I can go ahead and think about this as an improper integral. So my integral from 0 to pi over 2 on this function can't actually be tackled easily in Calc 1, but now we recognize that if I was to imagine a little value of t in here, I could think about finding the area from 0 to t, and then I could just push t towards pi over 2. Okay, so let's see what we come up with here. I'm going to be able to write this as a limit as t approaches pi over 2 from the left, and then I'm going to have an integral from 0 to t, my tangent of x dx. Now you might recall, as we had highlighted much earlier in Chapter 3, that the antiderivative of the tangent function is a good one to remember. That formula actually is negative natural log of the absolute value of the cosine of x. Now if you don't quite see that or don't remember that, remember you can always take tangent, turn it back into a sine over cosine, and perform a u sub to get back to this point. Now once I'm here, I just have to go ahead and evaluate my antiderivative. So that's going to make it a negative natural log, absolute value of the cosine of t, minus negative natural log, absolute value of the cosine of 0. Now fortunately this second portion here is going to simplify pretty nicely because the cosine of 0, remember, is 1, but the natural log of 1 is just 0. So that entire second term there is really just 0. The first term I have to think a little bit more carefully about. It can be helpful to think about my unit circle in this case. To think about what happens as the cosine has its input moving towards pi over 2, but from below. So if I was dealing with points on the unit circle, as I continue to increase my angle towards pi over 2, but I always stay below an angle of pi over 2, I can see what's happening to the cosine, or the x-coordinates of these points. The x-coordinates of all these points is going to be drifting towards 0. So really what I have here is the equivalent of a limit of a natural log. Let's come up with, say, a new variable, call it s, and the inside value there is really going to be moving towards 0, but notice always from above it. So again, all I'm doing here is I'm thinking about where the cosine is moving. The cosine was moving towards 0 from the right, and so I've just kind of swapped that out for a new variable. And now I can think about my graph of the natural log function, which I should know looks like this, crossing over the x-axis at 1. And if I move the inside of the natural log towards 0 from the right side, I'm going to be following the graph down this way, and so I know this is going to turn into negative infinity. Of course now, since I have negative infinity, I'm just going to end up with positive infinity. But regardless, I'll see that the total area here under this curve is infinite, or that the integral is divergent. So sometimes what's going to be a little bit more complicated with these type 2 improper integrals is that at first glance there's nothing to indicate to me that this is a new Calc 2 style question. Right? There's no infinity in any of the bounds, and so it can be very tempting to overlook this fact. I want you to actually see if you can go ahead and try example number 5 on your own. Can you explain to me what ends up being wrong in this integration down here? Why don't you go ahead and try to pause the video, take everything that we've learned so far in this section, and see if you can apply it to answering this question. Okay, so if you've tried to work through that question, then what you've probably have seen is that while again this doesn't look like a Calc 2 style integral, right? It looks like something I could tackle in Calc 1 with this easy approach. We should notice that our function, which would be 1 over x minus 1, is not continuous on the interval from 0 to 3, right? Specifically at 1, it's not continuous. And so I can't just use fundamental theorem of calculus right here to say, oh, let's just evaluate the antiderivative at these two different points. Instead, I'd have to take this as a Calc 2 integral. So I'll say here, instead, we would need to state that my integral from 0 to 3 should really be broken up into an integral from 0 to 1 plus another integral from 1 to 3. And I would have to evaluate each of these integrals separately, but I should note that each one of these is still an improper integral, now with just a discontinuity at one of the endpoints. Hopefully you were able to catch that. If not, it's something to be very aware of as you move forward. I don't know how often you've been checking the condition of continuity before you've actually applied your fundamental theorem of calculus, but it's been a very important and assumed thing that we've always been doing since Calc 1. So in Calc 2, with the introduction of an improper integral, it becomes even more imperative that we are constantly checking to see if our functions are discontinuous or continuous on the given interval, as that will drastically dictate what approach that we take.